Alright, I don't have a ton of time for this video because we gotta get this going before the video starts to crash. Because I know in the last video I ran the simulation, but you couldn't see it at all because the video was already not working. So anyways, so we're going to say k equals 0 and nx equals 10, and let's see what the video looks like. Takes a little bit to run, then at the end it's going to plot a video. And there we go. That's what it looks like. And now we can compute the L2 error for this one. Let me just copy this so that we can use it later. So here 0.35. Okay. So now let's up it to 20. See what we get. So again, of course, we're getting closer. Then we do the L2 error is going to be 0.18. And finally, let's bring it up to 40. And there we go. And now we do the L2 error again. Okay, so we look at what happens to the L2 error. So first what we do is we take the first one and divide it by the second one. So it's right around 2. A little less than 2, but it's right around 2. Now, 2 to the power of 1 equals 2, and we doubled the number of space intervals. Therefore, that implies that the order of accuracy of this method is approximately 1. And that's what you expect for k equals 0. You expect the order of accuracy for this method to be approximately k plus 1. Similarly, let's take, so we have this 18, that was the second. That was for nx equals 20. And then what happens if we double the number of space points? We go down to 0.9, and as you can see, that's going to be pretty close to 2 again. So again, we're getting the correct order of accuracy. And so that's good. That's exactly what we want here. So now let's up it to k equals 1. Let's bring nx back down to 10. Let's clear this so that there's not a whole bunch of stuff in the way. And let's run it. And here, if you look at it, this is really close. Now, before you could actually visibly see the difference because we are using constant functions. Here, especially where the exacts function, the orange function, is more linear, the blue function, which is the approximation, is very close to it. Okay, and so again, let's look at the L2 error. Nope. L2 error. Why is the sound on this computer? Oh well, let's just hope that no sound's ever happening again. Okay, so we got that. Now let's try it again for 20. See, it's very close still. And of course, by the way, if you saw any vertical lines in any of these, those shouldn't really be there. What it's plotting is those are actually gaps between the different those are gaps that appear between the different intervals. And so if the blue function was truly plotting the approximate solution, then you wouldn't see any of those gaps at all. Or you wouldn't see any of those vertical lines at all. And here, of course, we see this is really close. And this error, 0.0015. So let's go back up. So the first one we did for space equals 10, divided by the next one, space equals 20. It's about 4. And 2 to the power of 2 is 4. Therefore, the order of accuracy is about 2. And again, we do this for the next one. It goes down to 0.0015. And this, you can just see, is going to be 4. It's exactly 4 in this case, actually. So yeah, we're getting the correct order of accuracy. One thing I'm a little curious about, we start out with this 0.0242, and in the paper, if we look, we get 1.7 times 10 to the minus 2. So And so that would be 0.017. So for some reason my accuracy is slightly higher, but I'm still getting the correct order of accuracy. So that leads me to believe that maybe there is something with how I'm doing the initial condition. Maybe it's just like, maybe I'm doing something slightly incorrect, or maybe I'm just doing like the methods that MATLAB are using are slightly inaccurate. Whatever the case, because I have the correct order of accuracy, I'm not too concerned. And finally, just so that you can see this, if we go up to k equals 2 and nx equals 10, this is super accurate. Look, you can hardly see a difference between these. And then you can look at the L2 error on the side here. It's like 0.0012. So it's very small. So yeah, I wanted to make a separate video to actually show some of the visuals that you can make from this code. And it's nice because, of course, with me being more of a visual person, I like to be able to see these. And it's also good because we got to verify that this has the correct order of accuracy. And of course, I wanted to make a separate video so that I could actually get these videos to actually show up on the screen. So it might not be perfect, but anyways, yeah, we've essentially here gone from scratch and completely constructed a finite element method solver. And so if you want to do any sort of research involving finite element methods, or if you're implementing finite element methods on your own, hopefully some of the information that I use in implementing this particular method will be useful to you. And even if it's not directly useful, it still can be very educational to watch someone implement something like this and just see what it looks like and see how it works. But yeah, that's about all that I have on this project, and I'll see what other things I work on in the future, if there's other projects like this I end up implementing. Of course, it would have to be something that is entirely like published knowledge, because like all the stuff that I've done so far has been based on this paper, which is completely open. You can just Google it and download it and read it yourself, and you can go ahead and implement this method yourself. But yeah, I think it's neat to be able to show research level mathematics, and like show you how to take a research paper and actually work with it and build some of the things that they talk about for yourself. And so yeah, that's about it for this project, and I'll see you in the next video.